basics of time series. So essentially, even if you go back all the way back to 700 BCs, it's actually mentioned in the Bible saying that tell us what the future holds so we know that you're the gods. So you can already feel that time series has always been with us forever. And even back in the days, anybody who could forecast or somebody who is a forecast teller is somebody considered as a god. But in today's time, it's like they say, it's magical, but it's not magic. So essentially, forecasting is used in many situations. So you can think of building power generators plants in 5 years at an organization, or if we talk about a humongous organization like Walmart, we use time series in terms of deciding how we can stock the inventory more optimized in a more optimized fashion. And that is all coming in based on the historical patterns and distributions that we've been seeing, from the stocking department coming in from different Walmart stores. And then we also have one of the use case, which is about scheduling associates at Walmart. So we make use of, sorry, was there a question? Okay. So yeah, so about the scheduling associates at Walmart stores, it actually requires a lot of time series analysis. And we just don't make use of time series in that case, or a simple distribution of time series, but we also make use of other methodologies like computer vision and natural language processing. But all those combined together do form a time series distribution that we can, more sophisticatedly use to analyze large data set and can make optimized decisions like how we can schedule associates based on what is the kind of traffic coming into the Walmart, what are those peak times or the low times of the day or the week when we do really require a lot of associates, or we do not require, overkilling the resources that we already have. So the point here is Walmart is actually using time series in its day-to-day lives, and not just for one use case, but for a plethora of use cases. So you can already see that how much important time series is in our domain here at Walmart. And then when we talk about the predictability of an event or a quantity, it really depends on a lot of several factors. So by the end of this lecture, I wouldn't encourage anybody to take the information and just use it for stock market prediction, right? That would not be very wise, because it is not just one single time series that is playing an important role in terms of defining what's going to be the stock price for tomorrow. But there are other factors involved, such as political affairs, such as geographic affairs, such as other events or holidays which are coming into the picture. So it really boils down to how well we understand those factors that contribute to that domain. So there comes a very important information in place saying that you really have to have an expertise in the domain that you're working on. So that domain knowledge actually plays a humongous role in terms of developing a nice model or a good performing model. And then also really depends on how much data do we have from the history. So for models like, complex models like deep learning methodologies, you would see in the hands-on section that how well or how bad the deep learning model is doing, just because of the fact that we do not have enough data. Is there a question, anyone? Okay. It'll be great if everybody can have their mics on mute and keep the questions for later. That'll be pretty great. But then yes, then moving forward with how much data is available really plays an important role, just for the model to understand, analyze that what is the distribution like, what are the times of the week, month, or even the year when we can see some sort of seasonality or cyclicity in place. And finally, whether the forecast can affect the thing that we are trying to forecast. So usually it's a sequence to sequence model. So what does that mean is your current prediction will play as part of the input for your future prediction. So essentially you are going to forecast based on the forecast that you've just made. In other words, you could also say that you are essentially using the current error in terms of predicting the future forecast that would also have some sort of error associated in the previous time step. Moving forward, this is the first and foremost, like the first step for any time series analysis, where you basically get to see the different ETS decomposition of a single, time series distribution. So error, trend, and seasonality decomposition is very important in terms of understanding what the data looks like. So on the bottom, if you can see on the left, you have, the raw data set that is coming in from the thousands of passenger toy data set. And then on the right, you can actually see the decomposed series of that same distribution. And the 4 rows chart that you see up there are defined as the regular or the distribution. The first one is just the distribution that you see on the left. The second, which is a trend, essentially shows how the model or how the distribution is growing in terms of trend. Is it a growing trend? Is it a declining trend? As the time goes, is the business making more money, or is it going in the loss? Is something what the trend usually defines here. And then on the third column, you see the seasonality, which is again very much important piece of information that is coming in from this distribution that essentially shows is there a repetition or cyclicity associated with the dependent variable. So you can take an example of Walmart stores again, and if we look at the distribution of sales coming in from Walmart, you will see that there exists some sort of, or a very definite and obvious seasonality where you can see a repetitive pattern. And again, it really depends on the domain. And by domain, I mean there are several tens of departments within Walmart. So to be precise, we've got about 61 to 80 departments, depending on the store that you're going. And then each department has its own set of individual and exclusive distribution. So imagine a department like bread versus a department like, let's say, furniture will have different seasonality, will have different cyclicity, will also have different trends depending on the location that store is, the demographics of those stores, the size of the stores, and things that that store caters to the customer. So like, again, I'll be very pushing to the point where I'll be talking about how much domain knowledge is important. Without having that domain knowledge, it'll be hard for us to define good hyperparameters for the model, and eventually that model will not be able to perform better. So error, trend, and seasonality decomposition gives you a good idea that how does cyclicity or seasonality is playing the effects, how the trend is growing in the model. And if you see the last row chart, it actually shows the residual. So residual essentially is not of highest importance here, but essentially that can help an architect or a machine learning architect to understand where are those fluctuations or the piece, or in other words, noise available in the data. So any of those fluctuations that you see up here, you can directly relate to that data and can see, okay, so there exists some sort of turfs or peaks, and that's when you can see those kind of anomalous behavior in the residual. So having those all in place, it gives you a good idea how to begin with your modeling. And to go with the basic modeling of, in a time series distribution, you also need to understand what kind of trend does this model or this distribution have. So the trend can be defined as 2 different types of trends. Could be additive, it could be multiplicative. And then the additive model is essentially the model which sees the distribution and its trend in the linear fashion. So it's basically linear fashion. It's and in other words, if you see this distribution, if you see at this thousands of passenger graph, you can see that over the years we are just adding 10,000 passengers more. So there's no multiplicative effect coming into place. However, when we talk about multiplicative effects, it's basically to find or to identify a trend which is increasing or decreasing in a non-linear fashion. So those are the different kind of methodologies you have to keep in mind, because most of the models do require and demand from the architect or from the data scientist to explicitly mention what kind of trend that the person thinks is followed by this distribution. And hence, that's when the second row chart actually come into place, where here we can actually see it could be a linear, it could be multiplicative, but again, that again is a hyperparameter, and we can test our analysis based on that. Moving ahead, this is a very simple methodology for forecasting a distribution, which is called simple moving average. What it does is it basically calculates the average of the values within a selected bound range and the number of periods within that specific range. So the number of periods here essentially tells that how back in the past should be your window size, such that it can smooth out the distribution. So there are like a lot of I would say this is probably the most simplest methodology in terms of forecasting a distribution, but again, it may not give you the best results, because what it essentially is doing is it uses windows, and a smaller window size can actually lead to a more noise and more errors within the model, rather than showing the true signals that the distribution wants to show to the model. And it's also hard to balance the window size, because as you go smaller, you are being more accurate, and as far as what you are able to model from generalized time series. So with this, it'll be hard to reach to the full peak or valley. So like I explained, and you can already see here on your right-hand side chart, you've got 6 months simple moving average, and then you've got 12 months simple moving average, both denoted by orange and green. So you can see that the green will be much more smoother versus 6, because the window size is expanded there. So it can definitely capture the trend easily. But again, if you look closely, the seasonality is something which it's not able to capture. And the third weakness about this model is it does not really inform you about the possible future behaviors. So it really is using what has happened in the past, and that to keeping everything uniform. So it's not even using the weighted approach in this case. And to help to fix these issues, we then can actually introduce exponentially weighted moving average. So unlike a simple moving average, where it just takes a uniform approach across all the elements in one window size, the exponential weighted move rate actually introduces alpha smoothing term. So what it says is, it basically uses the alpha smoothing term for the immediate past observation, which is weighted more highly and more heavily than compared to the very last observation. And the factor that it gets decreased is exponentially raising. And as we go all the way to the end of our window or the entire distribution, the observation which has some sort of value, and that kind of effect that this value will have on this value is minimum as compared to the kind of effect this value or the immediate past value will have on the current value is totally different. So the way we do this is setting up an alpha value is again a hyperparameter, and this is again test and trial method. But you can already say that today's observation may relate better with last 6 months of observation than it would have some sort of correlation or heavier impact than if we go further than 6 months in the past. So that is exponential weighted moving average. And then the only problem with exponential moving average is it takes the account of the trend, but again, it's not able to take the importance or the effects of the seasonality available in the distribution. And that's when the Holt-Winters method come into picture, which is also called triple exponential smoothing methodology. So with this triple exponential moving methodology, you can already see that it's taking care of the three main aspects of that distribution. One is for the level, which is defined as L sub t. One is for the trend, which is defined as B sub t. And the seasonal component, which is defined as S sub t. So just to give you a little bit history about Holt-Winters. So Holt and Winters were two statisticians, and then Holt came out with a method which is called double exponential smoothing, which ended with just the trend that is B sub of t. So what really happened was he was able to capture the trend as close as possible, but the seasonality effect was still not introduced in Holt's method. And that's when Winters come, and then Winters was like, okay, let's just try with this triple exponential smoothing, and we can see that how well the model is behaving. And this all helped us because back then it was just EWMA until then, and that wasn't able to account for important contribution factors like trend and seasonality. And then we've already talked about the seasonal component methodologies of the additive and multiplicative, and depending on the data that you have, you can decide on those hyperparameters yourself. So to give you an example, and not going into much technical details, So those are the three different kinds of smoothing methodologies. So the single exponential smoothing just basically takes the alpha term and is using that how back in the future is your window size. And as further you go back in the back in the past, you will start realizing that not all values do contribute to the same extent. So hence we add the alpha term in there. Then if we move to the Holt's method, which is the double exponential smoothing, you can see that he already has, introduced two levels of methodology. So there you got the level trend, and then you've got the trend methodology. So you can easily capture the level as well the trend from that distribution. And then once we move to the triple exponential, Winters actually added or introduced the C sub t smoothing factor, which is essentially called the seasonal pattern. And then it was just LT plus BT. And then in the seasonal term, you simply multiplied the Holt's methodology with the Winters methodology, or the seasonal factor term. And then moving ahead with more, complex and more sophisticated methodologies. But in terms of understanding those methodologies like Arimas or SARIMAs, we really need to understand that how to set those hyperparameter values that Arima asks data scientists to set up, right? Now, the three parameters that go with Arima are P, V, and Q, which goes for the auto-regressive, the integrated, and the moving average. And for those values to be determined, we better use ACF and PACF. I'm sorry, there the spelling seems to be different, but it essentially is PACF. So autocorrelation functions and partial autocorrelation functions are essentially two methodologies for us to use in order to determine the right values for P and Q, at least. Now, when we talk about the D term, which is the differencing, we essentially set that value in terms of making a series stationarized. Now, I'll go through with all those terms that I've just used. So let's just begin with what correlation is. And it really is a measure of the strength of the linear relationship between two variables. And we all know as close the correlation is to +1, the stronger the linear relationship is. As close as it is to -1, the more negative linear relationship it has with the variable. And if it is close to 0, it really is not, or it really does not have any sort of correlation with the variable. Then if we talk about the autocorrelation, it basically is a description of the autocorrelation between the lagged values of a single distribution. And the partial autocorrelation is the autocorrelation between the YT and YT minus H, which is the past value of that distribution from that current observation. And again, you can set as big lag you want to go in the past, but it really is the linear dependency after removal of any, it really is autocorrelation after removing any linear dependency. And it really is the description of the direct relationship between the current observation and its own lag. And it will be a little bit hard to really get the idea of ACF and PACF and how do we go about setting those PDQ values using those different distribution plots that you just saw. But talking a little bit about Arima will actually help you to understand how we can really, set those values of PD and Q. But just to give you an initial idea, so all these different values that you see here, right, in both of these charts, it actually is the representation of the correlation factor of this current observation with its, past lag values. And here I've taken the lag values as 40 for ACF and 20 for PACF. You can go as, further down the lane you wanna, but again, the chart is just gonna get complex as you increase the lag values. And the shaded blue region that you see here is confidence interval. What it says is anything that is above the shaded region, the model thinks, and the confidence interval is set to 95%. And the model with that confidence thinks that this value is statistically significant correlated with the current value. So those are the kind of information we need to know before we jump into the Arima. And then once we talk about Arima, it's basically is again a forecasting methodology, which is a generalization of an auto-regressive moving average. where the auto-regression is the part that indicates the evolving variable of interest. So the Arima models are applied to series, which really show the evidence of non-stationarity. So what that means is non-stationarity is a data where the mean and the variance is not constant across the entire time. And we really need to bring the entire distribution to a certain place where the mean and the variance is constant, or the standard deviation is constant over the period. And this can be done easily by setting that value of D within Arima's hyperparameter, which is called as differencing. What it does is it basically differences the observation from the immediate next observation to get everything down in a, in a normalized fashion. So on the right hand side, you can see the original distribution of thousands of passengers. And once we use the differencing of just one, the distribution actually becomes stationary, where the mean and the standard deviation remains constant across the entire time distributed distribution. And this is something that we've already talked about, the integrated. And the moving average is a model that uses the dependency between an observation and the residual error from a moving average. So we've already talked about this a little bit with the PACF and ACF. So you can already see the similarity between these definitions and what ACF and PACF do. And then finally, the stationarity is something that we can achieve by the I term or the D term of Arima. Moving ahead, just to talk about a little bit of definition of Arima again here. So we need to understand that, what are these different pieces and how are these different pieces are coming into the pictures. So if we look at the auto-regression equation, so we've got this psi term here, and this psi term is essentially, it's more or less, it's an equation of the line, and all these are different, coefficients of the lag values, which are coming in from the distribution. And from the moving average, you can already see the eta term, and then here it's the error. So you again are regressing all those values, but essentially these are the error terms found from the historical distribution. And again, you've got the theta coefficient values associated with that. And again, it's at the end of the day, it's the equation of the line. So we've already talked about this, and then just to talk about a little bit of what happens when we try to make this model more complicated is something that you can see that this model is great when it comes to defining the linear terms and the distribution of the dependency between them, and also it's great to find the trend within that distribution again. But there was again a need of setting up this model in such a way that this model is not just able to take care of the level and the trend, but also the seasonal factor associated with that. And then if we go within the seasonal, if we can actually improve this model by having the seasonal terms associated, we have the SARIMA model. So it acts, for the first part, it actually acts very much similar to what the Arima does. So it actually takes the PDQ values within it, but the seasonal term actually adds the parameter of capital D, capital P, D, and Q, and then the M, which is again an important factor here, where P, D, and Q behave similarly like, the Arima's P, D, and Q. But Arima's P, D, and Q were only working towards getting the right equation for the level and the trend, whereas the capital P, D, and Q are the equations which can actually get you the best hyperparameters for the seasonal terms. And then the M is the number of observation in each seasonal cycle. So you could say that if you have a distribution coming in from a typical Walmart store, and if the distribution is a reflection of the groceries department, you can see that there is an existing seasonality between the kind of money that is, or the transactions between the customer and Walmart on a weekly basis. So people would be generally buying their groceries, during the weekends, probably like Saturdays or Sundays, and the least during the mid of the entire week. So that would be Wednesdays or Thursdays. So this kind of seasonal pattern need to be adjusted for making the model more sophisticated, and hence we have the SARIMA terms coming in place. Next, we move into a little bit more complex architectures like deep learning, where essentially an entire structure is an effort to imitate the human brains, where we have billions of neurons, each connected to each other by synapse. And here the synapse could be a layer or a connection between two different layers of neurons, and then those different neurons are passing some sort of information that they are learning through the entire process as the training is happening. And so essentially the training that is happening is letting the model understand the past behavior of the distribution with some extra regressors that could help the model to understand, how those regressors are affecting the sales peaks or the turfs. And then there are other factors that come into play, like the amount of data that we've had, for the purpose of training that we've already talked about. And deep learning methodologies do demand, humongous data resources such that they can understand the patterns better without being biased to the distribution. And again, the parameters, actually the hyperparameters in this methodologies are the weights, and those weights need to be adjusted in terms of getting that loss function as close to, or getting the loss function into a global minima, which is again a dream. But if we find a good local minima within that distribution of the loss, it'll be much better for the model to perform in an optimized fashion. But again, what is all the, what is that one thing which is essentially getting all those weights down to the local minima is something we call gradient descent. And we implement that gradient descent methodology using backpropagation. And then there's not just one gradient descent algorithm that comes into place. Again, that itself is a hyperparameter, and these all combined together behave like a huge search space. And that's when dealing with deep learning requires us having so many resources or high-end computers or even GPU cards in some cases. But then what we just talked about right here is called a kind of a deep learning methodology, which is called feed-forward neural networks. But if we have to make use of this methodology as good as possible, we go in terms of using the recurrent neural networks, which is another kind of neural network that deals with the time series distribution, where within these recurrent neural networks you will find cells. And these cells are basically the function of the input coming in from the previous time steps, along with the input that is coming in at the current time step. So you can think of these cells as kind of memory of a machine learning model, which tends or at least tries to remember what has happened in the past and how can I make use of that information to make the best decision for the future. Right. And then RNNs, again, are of different flavors and different architectures. The simplest one is called recurrent neural network. If you go about having more complex methodologies, you can have long short-term memory or gated recurrent units. But all these are just different ways of modeling a time series, and these are all need to be tested and evaluated based on the data that we have in order for us to decide that which one's the best model in terms of forecasting the time series. And then finally we jump into Facebook profit. So till now you must have realized that I've been paying most attention towards estimating the function distribution of the trend as well the seasonality and capturing those two pieces of a distribution as close as possible. But Facebook profit actually goes way ahead than all these state-of-the-art methodologies, where Facebook doesn't just introduces level, trend, and seasonality, but also introduces the effect of the holidays of that distribution. And the effect of the holidays is of the utmost importance, at least at Walmart, because we really have spikes and turfs that we see during those special events or special festivals that really come into picture. And if the model once told that, okay, here's the change point for this particular distribution that could affect the distribution of the sales, so the model really takes that into account and makes as good predictions as it can for the future. So on that note, I just want to say that Facebook profit has four main pieces. The first piece is a logistic growth curve trend. So this essentially, it could be done automatically by profit, where it can identify which point within that distribution is causing that anomalous behavior. such that that point could be considered as the change point, such that the model knows, okay, after this point, the distribution just changes its course of trend and seasonality, and I need to retrain my model from starting from this change point to make better predictions. And then we've got the weekly seasonal component, the yearly seasonal component, the monthly seasonal component, and the daily seasonal component. So it's just not taking the entire seasonality into account, but it's also making what kind of seasonality is the user trying to introduce or trying to identify from the distribution itself. And the cool part about Facebook Profit is the seasonality component is governed by the Fourier transformation order of the distribution, and we can simply optimize the Fourier order for whichever seasonal component that you're trying to optimize. And again, to decide which seasonal component you need to optimize or to introduce to the model, you really need to understand the domain itself, right? So not all distribution will be following all the three kinds of seasonality. May follow two different kinds of seasonality, but again, that is something that needs to be determined before we set all these values. And then finally, like I mentioned, the user provided a list of important holidays. And then it is not just holidays, it could be even events. So an event like Super Bowl, right? It's not a holiday, but it really plays a humongous, impact on forecasting Walmart sales. So a Super Bowl event will always be on a Sunday, but its effect could be seen on on that Saturday, right? So that Saturday, even though it's not a holiday, it's not an event, but it's still added to that data frame of holidays, which tells the model that, okay, here exists some sort of change point that may affect your sales coming in from the past. So Facebook Profit actually excels in that, and we will see in our hands-on exercise that how it compares with the performance when it comes to other methodologies. When we talk about the state-of-the-art Arima, SARIMA, single or double exponential smoothing, and then once we jump into deep learning, how are those models behaving versus how is Profit behaving? So and on that note, thank you, and I'll take any questions if you have here, and before jumping on to the hands-on exercise.
All right, thank you so much. You guys can either put your questions in the chat, or you're welcome to unmute your mic and ask, whatever's easiest for you guys.
Hello.
Hey.
Hi, I have two questions for you.
Mm-hmm.
Yeah, so my first question is, what do you think about, a regression model
Mm-hmm.
Versus a time series model, using a regression model to do time series problem? I'm asking this question because, in most of the Kaggle competition that I have seen, even with the Walmart forecasting competition recently, most of the winning projects is either using other gradient boosting model such as XGBoost or LightGBM or something like that. So what do you think about using regression to do time series?
Yeah, so by the way, good question. And then my answer to that is it's definitely and totally possible using linear regression models or tree-based models like even random forest or XGBoost or LightGBM, as you mentioned. So all you've got to take care in those scenarios is to make sure that your data really captures the time as one of the dimensions. So what I mean by that is the cool thing about these existing time series modeling methodologies versus non-time series modeling methodologies is the time series modeling methodologies already captures the date as they are supposed to be shown as one of the parameters within the data. However, with the tree-based methodologies, you really have to engineer that timestamp itself. So extracting the metadata of the time, having those metadata as part of the features, and if you would like, also have extra regressors. And till now, you've already seen, be it trend, be it seasonality, or be it the entire model. For example, Profit. Profit itself is a piecewise linear model. So if you would have, notice that for be it Arima, be it SARIMA, or be it Profit, and even the deep learning model, essentially all these models are forming an equation of a line. That's exactly what a deep learning model does. It's y equals to mx plus c in each of those cells. So it's forming an equation of the line, and it's trying to make the best decision for the best line of fit, right? And that best line of fit could be a linear fit, or it could be a non-linear fit. Whatever form of linear or non-linearity it follows, it still is fitting that line versus the actual values. And the least error that it finds with any of the line, that is the line which is considered as it has estimated the function of the distribution, right? So having said that, any model which again, you know, produces or depends on an equation of a line, which I think most of them are, can be used in terms of regressing a time series distribution. So all you got to make sure there is think of it as a cube, right? And if you slice a cube from any space, right? And if it is a time dimensional cube, you will still have the time as part of that dimension space, right? So as long as you form your data set in form of a time distributed cube, and if you take any observation within that cube will never leave its time dependency, right? And as long as an observation is not leaving its time dependency, a model can correlate that observation based on versus all the observation that it has seen in its history. If that helps.
Thank you for your answer. I have another question. What is the common practice at Walmart for the time series problem?
Sure. So another good question. That will be well understood once we move on to the hands-on, because the way I have set up my notebook actually shows a little bit of, actually has a little bit of flavor of the things that we do here at Walmart. It definitely does not have everything, but it can give you a sense of, you know, process that we put in place in terms of defining a model. So if you could just wait until then, and if you have any questions after that, I'll be more than happy to answer.
Yeah, thank you for answering my question.
Awesome. All right, so if there's no other questions.
I have a quick question, if you don't mind.
Sure.
Could you go back to that Facebook prophecy slide?
Yeah.
How do they, can you just elaborate a little bit on how they use the Fourier analysis? Like, is it to look at frequencies during the holidays, or to model out the volatility?
So we all know that the Fourier series is basically a combination of the cosines and the sinusoidal waves, right? And as we grow the order of it, we can make more complex distribution, you know, that we would prefer. So here it could be a simple grid search, depending on how far you want to go in terms of the Fourier order. So what it really is doing with each of those Fourier orders coming into the picture, it is forming a seasonal pattern, which is added again to the trend and the level order, which is again multiplied by the effects of the holidays. But again, not going into details. So what it is doing, it's forming different kinds of search space Fourier distribution. And it's looking at the one which is the most, how do I say, most close in terms of distribution to the actual seasonal component distribution. And then the way to decide what kind of Fourier order will be the most optimized, we set up a loss or a cost threshold. Now that loss or cost could be any of the metrics that are used within time series space, such like mean absolute percentage error or median absolute percentage error, or things like coverage, or things like interval width, or even confidence interval, or even AIC or BIC, or whatever criterion you want to follow. So having those in place, we try to see that which Fourier order from the training series is the best reflection in terms of forecasting the test series. And the one that we find, we again evaluate the model in terms of how well the model is doing. We make sure that there's no overfitting. And once that happens, we decide on the model with the right hyperparameters. Like, okay, so for the yearly seasonal, we could have 7 as order. We can see that this is a monthly distributed data, so it may not have weekly seasonality or daily seasonality. So we set them as false.
Okay.
Does that answer?
Awesome. Thank you.
Awesome. All right, guys. Sorry.
So I was just saying we have one question in the chat, or we can ask it after after your next section as well.
Sure thing. Just keeping time in mind, I think that it's the great time to jump into the hands-on. So if you could just give me a second. Okay. I think I'm not the host, so if I can be a host.
Yes, I can. Let me give you one mission. Okay, you should be able to share your screen.
Awesome. All right. I also see another question. Can I apply ANN for the time series data and how? Good question. Again, hands-on exercise will help you answer all those. So if you can see my screen, it's a vertical screen. Can somebody confirm that you are able to see the screen?
Yes, you can.
Are you able to see the presentation, or are you able to see the code?
Code.
See the code.
Awesome. All right, so going ahead with the hands-on, I just want to mention some of the libraries that come into picture. And again, these are not the only libraries. You will see some of the libraries associated with their unique cells. But to get started, I need some libraries that can help me to define some data and to read the data and process it. But before that, I do have two evaluation metrics. Like I said, mean absolute percentage error and median absolute percentage error. And why do I have those two is something that, again, I'll talk about. But then the third one is the stationarity test. And the way, so if you remember from ETS section, we really have to test the stationarity. Oh, no, this is the stationarity, not the ETS. I'm sorry. So this is essentially the test of the stationarity of the series itself. And if the series is not stationary, we really need to make it stationary before it is passed down to models like Arima or SARIMA. And then the way I do the stationarity test is by making use of AD Fuller package coming in from stats models. And yeah, so here we have the Walmart sales data. You can already see that in this data set, you have a bunch of different features like store, specific department, the date that is associated to that weekly sales. And again, weekly sales is the resampled weekly sales coming in from that store and department. We also have other features like whether on that day, was it a holiday or not, how much was the temperature, what was the fuel price on that day, the cost per index, and then the unemployment, and then again, the year, month, and week, engineered or broken down from the main date data type. So looking into just a little bit of modeling data here, we know that the data starts from 2010, February 5th, and it ends in 2012, October 26th. So we've got a total of 142 weeks of data, which again is not a lot. But again, this is coming in from the Kaggle. So somebody had a question about the Kaggle. This is the same data set. And then you've got the total weeks of 142, which is coming in from 45 unique stores and 81 unique departments from each of those stores. So a total of 3,645 time series you've got in this data set. But for today's project, what we're going to do is we have a total of 54 Walmart stores coming in from 81 departments. And we already know that this is a multiple time series. Although we're going to convert into a single time series, which will represent the sales of Walmart coming in from each store and each department, but now aggregated together such that it's not the store department level sales, rather it's Walmart level sales. So once we do that, this is a distribution that is coming in from this data set. So you can already see you've got some spikes and turfs at different times of the year. But again, there is a humongous spike during this time of the year and this time of the year. So if a wild and a good guess could be made, this could be, Thanksgiving time period, and this could be Christmas time period. And it again repeats next year, during the same time horizon. And then in the middle, you can already see that there exists some sort of cyclicity, within the data set. So the data looks nice. It has a nice distribution. It follows all the three things that we talked about in the trend and seasonality. So we can see a trend going down a little bit in the initial time and then picking up the speed going towards the growing period. And then for the seasonal component, we just by looking from the naked eye, we could tell that there definitely exists the seasonality within the data. And then the residual, again, may not be very much helpful, but the outliers can actually tell you the anomalous behavior, of that data, so that you can see that if there exists some sort of anomaly and that you want to correct before you jump into the modeling. Here, I think this is normal behavior, and those are the kind of outliers, and that is very much understandable because those are coming in from the special events and holiday times of the year. So right off the bat, jumping into the simple moving average and exponential weighted moving average, if I look at the 6 months and the 12-month simple moving average, I can see that as I increase my lags, the distribution becomes much more smoother, and as I decrease my lags, the distribution tries to capture the patterns, of the distribution. But again, this is one of the most simplest method where we are basically just averaging the past couple of values to identify today's value. So it may not be able to, reach to its highest potential where we could expect it to capture the peaks or even the turfs within the data set. So you can already see, it's not able to capture the actual ground truth as close as possible. But once we move to Holt-Winters method, it's basically triple exponential smoothing. I'm sorry, this should be triple exponential smoothing, where we are now introducing the trend and the seasonal effects within the data. And you can already see that Holt-Winters method versus the EWMA 12 lag method is performing a little bit better, and if there is a way that we can make it better by using different complex methodologies, that we'll see in the further cells. So now, before jumping into the more, complex methodologies, we gotta check for the stationarity. Again, I'm using the Dickey-Fuller test. And according to Dickey-Fuller test, it says that the data has no unit root and is stationary. Although we can see, looking at this distribution, that it definitely doesn't look stationary. So what is Dickey-Fuller test really doing? All you gotta check is for the p-value here, right? And the p-value, in most cases, it's set to 95 or 5%. Again, this value is not very convincing. It's not as small as I would think it would. So again, I would definitely go ahead and make it stationary by differencing it. But before that, I want to see that how do ACF and PACF plot look like. So if I just look at the lag plots between YT and the YT plus 1 value, there is just a little bit, there exists correlation, that's for sure, but there is not a huge correlation, as we go ahead and go all the way back to the values that are in the future, all the way further in the future. So we would see that the existing correlation really is very tightly coupled between the neighboring values. And this is what the partial and the autocorrelation plots show. So now you gotta realize that partial autocorrelation and autocorrelation is not very simple to understand or to read or let alone finding the right hyperparameters values from these two plots. The reason it's difficult is it comes with a lot of rules in place. So what it says is, it looks at the distribution of both of these plots. It looks at the distribution of autocorrelation, and it looks at the distribution of partial autocorrelation. And what it tries to identify is it looks at the distribution and try to see whether the distribution follows a geometric distribution or whether it just falls down until some peak lag values. And based on those different rules in place, we decide whether we should develop AR methodology, or whether we should develop MA methodology, or we should develop Arima methodology. Now, to understand those, I will send this, like I will have all this up on my GitHub, which I'll share with you, but also there under the README section, you can find different, resources that I'm talking about to understand how to really identify the values of the AR and the MA using these two different plots. But to make it more simpler, and the things that are done more common in in data science world is by setting up a grid search or a Bayesian optimization methodology to select the PD and Q values. So in order to do that, we just divide the data set into two sets. So I've taken a subset of data starting from 2010 to 2011 as train, and the rest of the 2012 as test. So you can see the two different data sets. And then I use the Auto-Arima, and again, Auto-Arima, you can think of Auto-Arima as an optimization package for Arima that actually tells you that what is the right value for PD and Q for that specific data set. Once I use 0, 1, 1 as defined by this Auto-Arima, I just get horrible results. And again, if we go again here, I can talk about how did Auto-Arima come out with 0, 1, 1, but again, knowing time limit, I don't want to go into all that details. But just assume that we gotta do some sort of optimization methodology such that we can figure out that what is the right value for PD and Q. I did that offline. So I had these values, and you can see that the Arima model is okay in terms of predicting versus the the exponential methodologies methods, but it's still not quite there as we would like the model to be performing. So by adding the seasonal term into the Arima, what we are doing is we are basically adding the seasonal order, the capital P, D, and Q, and then the M term for the seasonal. So I think that since this is a weekly distributed data set, I think having a weekly seasonal lag would make more sense in terms of forecasting this distribution. And once we do that, you can see that the green distribution is what the SARIMA follows, and it definitely is able to capture those kind of differencing or the distribution versus the Arima model. Again, this is a little shifted. I would just have to shift a little to get it back to its right place. But if you just look at the two evaluation metrics coming in from Arima and SARIMA, the metrics being MAPE and median APE, so you can see Arima is performing at 6.47 and 5.23 MAPE and MDAPE respectively, and SARIMA is definitely a better performing model than Arima. So that gives us a nice idea that okay, having seasonal and trend both in place using SARIMA can actually develop or help us develop a better model. Now, going to the deep learning methodologies, and again, one of the questions was, can we use artificial neural networks to forecast? Yes, you can. And the way you do that is by feature engineering some of the data sets, or some of the entire data set in such a way that it can be represented as a sequential model. And now there are different ways to go about it. The different way to go about it would be having engineer your date time as part of your features, and then you can also add other regressors within that entire matrix. But I've taken a simpler approach here where I am just taking a series of data that essentially starts from the first location all the way to the right before the last location. And so what essentially it is doing, it's basically making use of today's sales in order to predict the next day sales. So that's all it is doing. And that was the most simplest way that I could build this model for this presentation. But again, I'll be thrilled to see how well you can engineer the data and can outperform this model's capacity. So looking at this model, again, this model is not hyper-tuned. This model does not have enough complex nature. This model also does not have enough features to help the model to understand the variance of the entire data. But if we just use the rudimentary model with the basic default set, or not the default, but the basic settings, we are not able to see, a nice capturing, distribution coming in from this model. But even though that is in place, we can still see that this model is outperforming the SARIMA just because of one reason, that it is a very simple model that almost presents the average value, but in some cases it captures those peaks. So the difference between these two, distribution is not that big. So definitely just don't go by the numbers. Always look at your distribution and start comparing with different models distribution to make your right decision on that. But now if we go into the more complex methodologies like LSTM, and I've put some resources here for you to understand how LSTM works in details. Doing the similar methodology, but the only difference is now LSTM model have the capacity to add a memory unit within the neural network. Unlike the regular feed-forward neural network does not have any memory per se, but LSTM actually tries to learn and to use that learned knowledge to make the better future forecasts. And once we do that, we train it for about 100 epochs. And then you can already see that how well the model is able to capture the, the distribution of the ground truth. And then once we start looking at the evaluation metrics, you can see the LSTM MEP and median APE is way lesser and performing way much better than any of these models. Although there is a big problem with this neural network built above. This will be a kind of a homework, and please let me know if you have any questions. But I can already tell that if you find that problem, and there's a problem in this, and I always keep that as a homework. And once you figure out that problem and you rerun the model again, this will change, definitely. This will not be able to perform as good as it is doing right now. I can already tell that there is some sort of cheating going on in the model, and that's the hint. So the hint is the time series forecast, it should never be based on the ground truth. Now figure that out in your free time or after this talk, that what is that problem and how can we, take care of it. Now moving to the profit model. The profit model is basically just an import from the profit library, but again, profit itself is a big model that you can be expert in. So what it is doing, it's basically getting the profit model in place, and the way it expects the data, it demands the date time feature to be named as DS, whereas the dependent to be named as Y. So the date gets to DS, weekly sales converts to Y. And then we did not optimize, again, any of the seasonality here. That, again, it is a homework where you can actually set up a grid search and optimize this model as close as good as possible, and see how well the model is performing with those optimized set of values versus this normal model, which is just using the default settings. Now, like I already said, that once this model is trained, you basically make use of the model to forecast the future sales, right? Now, the way that is done is we already know that the sampling value of the ground truth is set to weekly, and Walmart week starts from Saturday. So we always set the frequency to the weekly, which is starting from Saturday. So Saturday will be the first day of the week for that specific week at Walmart. And once we have that, we forecast the entire distribution. And then we look at how well the model is doing versus the ground truth. So the blue band that you see is the interval width of the forecast, and the black points that you see are the ground truth value. So you can see the model is able to capture even the highest peaks and the lowest stuffs in some cases. And we can from here make a better decision that how well the model is doing. So if we have to see how well the model is doing in terms of the error terms, this is where the profit model is sitting. And again, looks like the neural networks have beaten this model. But again, like I mentioned, there's a problem in the neural network, which you can, identify once you start working on the script. Figure that out, see how well the model is doing once you set up those, equations in place, and then again, compare this methodology. The last thing that I want to say before I conclude is, you must have noticed that till now we are working on a single time series, which is right here, right? And that's because we resample the entire Walmart sales as the weekly sales. But what if we do not want to use a single time series and would like to forecast from the store and the department level sales? So I have already created this feature list here. So that is the second task of the homework, where I would ask you guys to build a model that could be used to forecast the multiple time series instead of single time series. So in this project, now you're forecasting each store and each department sales versus just Walmart sales. And the number of time series that you will be forecasting will be 3,645. Don't be, don't be scared of this. It's a simple project. And like I said, put some time and effort in terms of understanding the problem. And if you have any questions, always feel free to email me or text me, and I'll be more than happy to help you out. So on that note, I would conclude my today's presentation. And if anybody has any questions, I'll be more than happy to answer them.
All right, thank you so much for your time and for your presentation. We have one just general question in the chat, just asking about sharing the link to the notebook. Is there any way you could send that in the Discord channel?
Oh, yeah. Okay.
Perfect, okay.
Hey, hi, I do have one question.
Hey.
So as you said, there will be 3,650 time series, right? So how much computational power do you require generally in that case, or generally how does Walmart do in such cases?
Okay, so whenever we talk about multiple time series, we are basically talking about way more multiple time series than we just saw here. So we'll be talking about some tens of thousands of different time series, and that too coming in just from a small project. Now, like you said, with increasing time series, we definitely are looking at more computational power. So if you just want to go by going with the brute, so there are different ways to model a multiple time series. I would start that way. There is definitely a brute force method where you can simply run a profit model in a for loop for each of those combinations, or you can make use of a little bit more of sophisticated methodologies where you can probably cluster stores or probably cluster departments such that you have a homogeneous set of stores, you have homogeneous set of departments, you have similar distribution coming in from each of those clusters. And this is just one solution. There are other thousands of solutions, but this is one solution that in the early ages, in the early times, we tried at Walmart, where we had the set of homogeneous stores or clusters. We had, a very much similar looking distributions coming in from those clusters, and then making use of those similar distributions to form models cluster level, such that we are not, going overboard with 3,000 models. Rather, we can just have maybe 6 models that are coming from 6 clusters, if those are the number of clusters. So there are different ways to model these. That's what I'm saying. Try to spend some time, think about the problem. It's not a crazy data set. It's a relatively very simple data set. See how you can, find a solution. And really, if one of your solutions look nice to me or to my team, we can have more conversation of the things that you've done in this project. But again, try and let me know if you have any questions. I'll be more than happy to help.
Okay, if you have few more seconds, I would like to ask one more question.
Go ahead.
Why are you using MAP as a metric and why not others? And how often do you use all deep learning models, or it's just like in the final situation you use deep learning, or it's even before any data, or like you start with SARIMA and then go to deep learning in the final production stages only?
So yes, if there is a project which has never been touched before, and if the project deals with time series, we'll definitely be starting with our baseline solutions or methods. And the baseline methods, usually start from Arima in our case, and testing with Arima, SARIMA, and seeing how well the model is performing in those scenarios. And if there is a room for improvement, we definitely do not use deep learning all the time, but that is definitely a model which sits in our baseline. So we always make sure that whatever different models that we have in our toolbox, we try and test them and see that which one has the highest potential to get deployed. And again, there are different trade-offs. So for example, let's say an LSTM model is performing at, say, 1.2 MEP, for example, and a profit model is sitting at 2.8 MEP. Of course, LSTM is better, but we also have to see the requirements of the business. We also have to see the requirements of the production. And we also have to see the complexity after the production. And again, we also have to see the lifetime shelf, or the shelf life value of that model. Making or having those decisions in place help us to decide that which model we are going to go for. For your second question, why am I using mean absolute percentage error? Again, there are other hundreds of metrics that you can use, but usually in time series, mean absolute percentage error or median absolute percentage error are used, and that actually helps us to compare different models in an orange to orange state, right? The second reason that we go with these different metrics is also comes from the business. So the business helps us to work on a project by giving us a problem. And then if exists or if there exists a solution coming in from the business may have had their models evaluated based on the MAP metrics. So now, since they already have calculated using MAP, we need to also be on the same page such that we can compare the performance of our models with their models. But again, there are other hundreds of metrics that you can use, so feel free to use any of those that feel you better.
Thank you. Thank you very much.
Yeah.
I had a question. So since you mentioned different like you start off from the basic models to find out which is the best model. So for our Walmart question, is it necessary for us to show the progress we have made through each model, or do we just have to show the best model to you?
It'll be great if you, because either way, you will be developing models. And in that process, if you can just simply keep recording their performance and have them all in one data frame, and at the end, just plot those different, performance coming in from each of those models. It'll be great because having all the solutions within just one data frame will be helpful, not just for you to understand, but also for somebody else who is evaluating your results.
Okay, so the visualization in terms of that would be like sufficient in terms of showing it the way you had expressed in your models. Like what I mean by that is we can explain the models to you rather than writing those down, right? Like jotting down the disadvantages or the advantages.
Oh yeah, absolutely. So
Okay.
as long as the visualization is just the comparison visualization, that should be more than enough.
Sure, thank you.
All right, do we have any more questions?
Hi, could you detail me over how you're choosing the P and the Q variables for the Arima model? And my second question is, can I use some kind of for loop to arrive at the the number of hyperparameters I'm choosing, which gives me the least AIC and the SIC?
Right. So that definitely is one method that I think everybody uses in today's time and period, which is the simple for loop grid search between P and Q values for Arima. But if you don't want to use that, and for some reason you really want to go with the ACF and PACF plots, again, you really need to understand the different combinations of the values that make you arrive at the right value of AR and MA. So you need to mention, or you need to understand the distribution of ACF and PACF. And within those distribution, you also need to understand whether the ACF is following the geometric or just P-lag, or is PACF following the geometric or P-lags. And based on those combinations, there are rules in place saying that if this happens, let's say if ACF is following geometric and PACF is following the P-lag, then you use the AR term. If it is opposite, then you use the MA term. And if it is both of them are following geometric, then you use AR and MA terms. And then this is the first stage to decide which term you're going to use. Once you decide on the term, then you again have to look into the plot to see that which is the cutoff for the right value for those AR and MA terms. And that just becomes very painfully, long process. And hence you let the machine do the job itself. And you correctly mentioned saying that you can use a for loop, and then you can start comparing either of AIC or BIC values. And based on the different hyperparameters, you can select one which performs the best.
All right, thank you.
Yep.
All right. Let's see. Just one last question. Where can I find the notebook? I believe we're going to post a link to it on the Discord. Is that correct?
That's correct. Right after this talk, I'll put everything on my personal GitHub and we'll share that on Discord.
Perfect. All right. Well, thank you so much for your time. Thank you so much, Walmart, for coming, supporting Datathon, and providing this class for all of us. I know it was very interesting and helpful for me. I'm sure it was for all of our participants. So thank you so much for your time. And if you have any more questions, Walmart will be available on our Discord for a little bit. They have a channel. You can also join one of our sponsor rooms to potentially talk to them. And thank you guys so much.
Thank you, Jonathan. Thank you, everyone, for attending. I really had fun, and I really hope that everybody took something with them with this talk. And if you have any questions, I'll be posting this GitHub link and other resources on Discord, and feel free to chat there.